Hey everyone, and welcome. Today we are going on an incredible journey into the secret life of metals. We're going to see how they go from just being humble rocks in the ground to becoming the very materials that build our entire world.
Seriously, have you ever thought about it? That sleek metal phone in your hand started out as a chunk of rock. The process that makes that happen is a fascinating field called metallurgy. And it is this amazing blend of chemistry and engineering that is, quite literally, shaping everything around us.
So here's our roadmap for this adventure. We are going to follow a metal's epic journey, right from when it's locked deep inside the earth all the way to becoming a superpowered material we can actually use. Let's get started.
Okay, so first things first, what exactly is metallurgy? Before we can really follow the journey, we gotta know what we're talking about, right? So let's start with the basics.
To put it simply, metallurgy is the science of getting metals out of the ground and then making them useful. This covers the whole shebang, from finding the right kinds of rock to purifying the metals and even mixing them up to create brand new super materials called alloys.
All right, our quest begins deep inside the Earth's crust. But we can't just start digging anywhere we want. We're on the hunt for very specific rocks that are packed with the metals we need. And this brings us to a really important distinction: the difference between a mineral and an ore.
The key difference here, it all boils down to one thing: money. A mineral is basically any naturally occurring metal compound, but an ore is a mineral that has enough of that metal packed inside to make it actually profitable to mine. That's the treasure we're really looking for.
Here's a great way to think about it. All apples are fruits, but not all fruits are apples. Same idea. We're on a very specific treasure hunt for those high-value, profitable minerals that we call ores.
And here's some of the heavy hitters, the most wanted ores in the world. For aluminum, the big prize is bauxite. For iron, which is like the backbone of all modern construction, it's hematite. And for zinc, the stuff that protects our steel from getting rusty, we are looking for zinc blende.
So we've found our treasure, we've got the ore, now it's time for a major cleanup. The problem is, the ore is still mixed with a bunch of junk: sand, soil, rock. This stuff has a name. It's called gangue. Our next mission is to concentrate the ore by getting rid of all these impurities. Now, there's a really clever way to do this, especially for sulfide ores, like that zinc blend we mentioned. It's called froth flotation. You can basically think of it as giving the crushed ore a bubble bath. We mix it with water and pine oil, then blast air through it. The valuable metal bits stick to the oily bubbles and float up in a froth, while all the worthless gangue just sinks. Then we can just skim that concentrated ore right off the top. Pretty smart, huh? Okay, we've got our concentrated ore, but the metal is still chemically locked up inside a compound. The next step is probably the most dramatic part of the whole story: a trial by fire. It's designed to break those chemical bonds and finally free the crude metal. The two main methods here are roasting and calcination, and the biggest difference between them is the air supply. See, roasting heats the ore with tons of air, which is perfect for turning sulfide ores into oxides. Calcination, on the other hand, happens with no air around, and it's used for carbonate ores. But either way, both processes get us to the exact same critical point: a metal oxide. So we've made a metal oxide. Now what? How do we knock that oxygen off to finally get our hands on the pure metal? Well, the answer depends entirely on the metal's personality. How reactive it is. And we can figure that out using the metal reactivity series, which is basically a power ranking for metals.
And here it is. Way up at the top, you've got the most reactive metals, like potassium and aluminum. These guys hold on to oxygen for dear life, so it takes a ton of energy to separate them. In the middle, you have your workhorses, like zinc and iron. And down at the bottom, you find the least reactive, almost noble metals, like silver and gold, which are way easier to isolate. So this power ranking gives us a clear game plan. For those super reactive metals at the top, we have to bring out the big guns, the brute force of electricity, in a process called electrolysis. For the metals in the middle, we can use a cheaper chemical helper, like carbon. And for those really chill, laid-back metals at the bottom, a lot of the time, just heating them up is enough to set them free.
We did it! We've extracted the metal. But hold on, it's not quite perfect yet. This crude metal still has tiny amounts of impurities that can mess with its properties. So it's time for one last step: the final polish, a process we call refining.
A really common and super effective way to do this is called electrorefining. Just imagine this. We take our impure block of metal and a really thin starter strip of pure metal, and we stick them in a special chemical bath. When we run an electric current through it,
The pure metal atoms actually leave the impure block, travel through the solution, and plate themselves onto that pure strip, leaving all the gunk behind. This process can get us metal that's over 99.9% pure.
Okay, our metals journey is almost over. It's pure, it's ready to go. But what if we could make it even better? Maybe stronger or lighter or more resistant to rust? Well, we can. And that's where we give it a whole new identity by creating supermetals called alloys.
So what is an alloy? It's just a strategic mix. The best way to think of it is like baking a cake. You start with your flour, that's your main metal. Then you add other ingredients like sugar or eggs. Those are other metals or even nonmetals to create something brand new with totally improved properties.
And you can see the power of alloys right here. You mix some aluminium with a little bit of copper and magnesium and bam, you get duralumin, which is strong and light enough for airplanes. Or you add some chromium and nickel to iron and you get stainless steel that won't rust. Every single combination unlocks a new superpower for a very specific job. All right, let's do a quick knowledge check. Pop quiz. What was that one huge difference between roasting and calcination? Think about what was in the furnace. It was all about the air, right? The presence or absence of excess air. Okay, next question. Let's try to connect a couple ideas. We know we use carbon to reduce iron ore, so why can't we do the same thing for aluminum ore? Remember that power ranking? Where does aluminum sit? It's way up at the top. It's just too reactive for plain old carbon to handle.
And one last question for you. What is an alloy, and can you give me an example we talked about? One alloy is just a mixture of metals, and a perfect example is stainless steel, which we use for everything from our kitchen forks to surgical tools, all because it's so good at resisting corrosion.
So the next time you pick up your phone or use a stainless steel fork or even just look up at an airplane in the sky, I want you to remember the incredible journey it all took, from a simple rock through fire and electricity to become that useful, amazing object. That is the secret life of metals. If you found this useful, like, share, subscribe, and don't forget to press the bell icon